Hi, class. We're doing one more section in Chapter 8 today, um, which is on a thing called the method of Frobenius. So, what we've seen earlier is how to find series solutions to an equation like this one um, around what we call ordinary points. And ordinary points, as opposed to singular points, are basically points where those coefficients, p of x and q of x, are, let's say that's points where p of x and q of x are analytic. And analytic is a class of functions that is basically just like nice. It encompasses, trig functions and polynomials and rational functions as long as the denominator is not zero. So another way we can think of this is just that they're nice enough. Nothing weird's going on. They're defined at that particular point. Okay, so we're just talking about the function at a point. Um, so, like a rational function maybe is analytic everywhere except for where the denominator is zero because it's a property at a particular point. Now, we're skipping a couple sections just in the interest of time. And section one of the sections we're skipping is 8.4, which is some theory about how if you have um, ordinary points, then you can always then the series solutions always exist. Um, but we're concerned about what if we don't have an ordinary point? What if we have some point of our equation um, that is actually a singular point? And you might be thinking, well, if you have a singular point, then you can't, you're dividing by zero, maybe. So how does that even make sense? And it's not necessarily that it makes sense at that point, but we care about what's going on around there. And so imagine, your concept of the singularity. There's something like a black hole happening or something really really bizarre happening. Maybe you're dividing by zero and you're blowing up, everything's going crazy. But it would be nice to know what is happening as you approach that point. And that's exactly why it's important to find solutions around singular points, because that's really where all the interesting stuff is happening. So what motivated this theory is the Cauchy-Euler equation, which we've seen before. And this is what this looks like. And actually, this is defined for x greater than 0 um, so remember the theory that we had for this, or let's think about what this looks like if we put it in a standard form, right? Because the standard form we had up there, there's nothing up in front of the y double prime. So in this case, our p of x is equal to b, we have to divide by ax squared. So we get b over ax, and our q of x will equal, it's the thing over in front of the y, so we get c over ax squared. And so, using the theory we had before, this doesn't really make sense at x equals 0. Because we can't plug in x equals 0, but we care about what's happening, immediately after x is 0. And we saw this equation before back in chapter 4, and we also skipped a section on it in 8.5, just because, again, in the interest of time. But what we saw in chapter 4 is that the solutions look like y equals x to the r, where r satisfies a special version of the characteristic equation that we called the indicial equation. So we had r satisfies, and this equation looked like r times r minus 1 plus b over a r plus c over a, something like that. Equals 0. And so the reason that this worked out is that if we plug in a power of r into this Cauchy-Euler equation and we start taking derivatives, the derivatives of this power function end up canceling out the um, like sort of x squared and the x there, which are the things that are causing the singular points. So the notion here is that if we have singular points that we can kind of cancel out through our derivatives, then maybe we can find solutions kind of like we did for Cauchy-Euler. So let's be a little bit more specific about this. So this is our equation again, where we'll now assume that x times p of x and x squared times q of x are analytic functions. So in the Cauchy-Euler equations, in the Cauchy-Euler case, we assumed that these quantities x p of x and x squared q of x were constant because then that put us back. Remember back in chapter 4, we really wanted things to have like constant coefficients. And so like in that special case, where the x and the x squared would sort of cancel things out and you'd just be left with constants. So now we're sort of assuming that that this x and x squared will leave us with analytic functions. So earlier in this video, I sort of described analytic functions as being like these nice functions. But the definition really is that you can express them as a power series. And so what that means is that x times p of x equals a power series, p naught plus p1x plus p2x squared. So this is about 0, right? That's the point that we're concerned about here. And we can write this generally as in the summation notation. And then we can do the same thing for x squared cubed. So remember, we're concerned about what's going on near 0. But near 0, all of the higher order terms are going to be near 0 because they've got an x in them. So if you plug in some super tiny number, it's going to almost kill off all the terms except for that first constant term. So that means that we have this limit as you get closer to 0 of xp of x, you just get that first constant p naught, whatever that happens to be for the power series representation of xp to the x. And same thing for q. So that means that xp to the x is an analytic function, but near 0, it's really very similar to a constant, and same with x squared cubed of the x. So then the idea is that near 0, this function is going to behave like the Cauchy-Euler equation. And what are the solutions to the Cauchy-Euler equation? Well, they're y equals x to the r. So the guess here is going to be that instead of our solutions being like a constant times x to the r, it's going to be xr times an analytic function. So that's sort of the basis for this theory. And so what we're going to do now is we're going to sort of define what it means a little bit more rigorously, this assumption up here, and then take our guess and plug it in and see what happens. All right, so let's start off now with definition. So we have our regular equation here, and we've already seen what a singular point is. So it's a point of p where p of x and q of x are not analytic. We saw that in the previous chapter. And so now we're going to sort of modify the concept of singular point. We say a singular point is said to be a regular singular point. And that's if we have what we were just talking about. If you can kind of multiply it by x or x squared by and fix that singular point. So what that means rigorously is if both. So now we're not necessarily talking about. Oops, I forgot something. I forgot to write x naught. So we're talking about our singular point x naught, which before we were assuming x naught was 0, and now we're taking an arbitrary point. So instead of x and x squared, we have x minus x naught. That's like kind of the center. So if both x naught, x minus x naught times p of x and x minus x naught squared times q of x. And so if we can multiply by these factors and that fixes the functions at these points, by which I mean they are analytic at x naught. So that's what it means to be a singular point. If you have a problem at that point x naught, but you can fix that problem with a factor of x minus x naught. So otherwise, we say it's an irregular singular point, obviously. So there are a couple questions in the homework where you can use this definition to determine or to classify the singular points of the equation. And there's examples in the book of that as well. Okay, so now what do we do with this? Now let's assume that we've got a regular singular point to our equation. So we've still got our equation. Let's make this small. And we'll call this equation, I don't know, star. So I'm going to assume that x naught is a regular singular point for our equation star. So I said before that our guess is going to be that our solution is going to look like x to the r times an analytic function. So we can write that like this. So we're going to call it w of r comma x, because it's a function of x, of course, but then it's a function of r too, because we don't know what r is. So we can kind of like, we know it has this form, and then we're going to try to figure out what r is. So we can write it like x to the r times a power series, because a power series is an analytic function. And then we can rewrite this. We can pull that x to the r in. So this looks like n equals 0 to infinity a n x to the n plus r. So we need to figure out what all of the coefficients of an, all the coefficients an, and then also what is r. And once we have those things, then we'll have our solution. So we'll see if we can figure out what they would need to be. So we can differentiate with respect to x. We get w prime being differentiation with respect to x rather than with respect to r. So that's easy enough. We just do our power rule, and we can do the same thing with the second derivative. So I'll write them out. All right, so the next thing we want to do is plug this into star, but we're missing a couple of terms. We're missing p of x and q of x. I mean, we have them. We can just write them, but it would be nice if we could write them out in power series form. So let's think about them. We assumed that x equals 0 is a regular singular point, which means something about p of x and q of x. And in particular, it means that x times p of x is analytic. And analytic means you can write it as power series, so we'll do that. It equals, we'll call its coefficients p n x to the n. Now we can divide by x to get p of x by itself, because that's what we have to plug in. And that's easy enough to do in power series notation, pn to the xn minus 1. And this might seem a little confusing because you're like, well, but p of x is an analytic. And so you can't, it's not analytic at 0, so you can't write it as power series. Well, this is not exactly a power series because that first term is an x to the minus 1. But that's okay. The notation is still valid, even if it's not a power series. So then we've got the same thing for q to the n, which I'll write out. So now we've got all the terms to plug in, and I'm going to still make this smaller yet so that I have the equation star on the screen. And so when we plug in, it's going to look like this. So this is gross because we have like we have multiplication of infinite sums. And we know how to do that in theory. We can sort of start writing it out. So we can do like the Cauchy product and multiply things together and group everything by x. And we couldn't do this. It doesn't necessarily have a nice pat format, but we can do it sort of term by term. So the lowest term is going to be an r minus 2, which is what you would get when n equals 0. And what you get, you can confirm all the details of this, but it's going to look like this. R times r minus 1 plus p naught r plus q naught times a naught x to the r minus 2 plus our next term is going to have this r plus 1 r a 1 plus r plus 1 p naught a 1 plus p1 r a naught plus q naught a 1 plus q1 a naught to times x to the r minus 1 plus a bunch of higher order terms, and that's going to all equal 0. Now, remember the way that we do this is if this sort of infinite series, this kind of power series is equal to 0, then all the coefficients are going to be equal to 0. And so in particular, this first coefficient has got to be equal to 0. We can assume that a naught is not 0 because it's the first term of our power series of what we're assuming W is, right, up here. So back when we did that, if it was 0, then we would just, shift R up and we want that power series, we want our guess to start with a non-zero number, otherwise we could just change that. So really up here was where we were making the assumption that the first term is non-zero, okay? So that gives us that in order for this solution to work, we're going to have that quantity, this quantity in brackets here, equal to 0. And so this is called r minus 1 plus p naught r plus q naught needs to equal to 0. And this is called the indicial equation. And I'm going to write this out in a little bit more rigor in a second. But remember, this looks like the Cauchy-Euler indicial equation. It's kind of like that characteristic equation. And that's how you find R. It's how you find the R that's going to work for your solution. So let's write that out now rigorously. And exactly what we derived before, that equation is called the indicial equation. And then the roots of that equation, what the values of R, so that's the R values, are called the exponents or the indices associated with that singularity, because those are the R's that give you the form of your solution. Now, one more thing to point out, what these P naught and Q naught, how did we get those? Well, that comes from the way that we had them before was from the power series representation of P naught, or of P and Q. Because x naught is a regular singular point, we have that x minus x naught times P of x is analytic, and so that equals this power series P n x to the n. And P naught, this definition here, this limit, is exactly what you get if you sort of, oh, sorry, I wrote this wrong. It's not x to the n, it's x minus x naught to the n. And so if the limit as x goes to x naught of this expression, all of the terms go to 0 except for the p naught term. And so that's exactly what you're getting here. So that's where that definition comes from. And same with q naught. It's just the first coefficient of the power series representation of x minus x naught squared times q of x. Okay, so what I'm gonna, so we basically figured out how to find a solution to our equation. So let me stop here. I'm gonna stop this video, and I will do one more video from this section where we sort of summarize everything with an example. So we'll see you then.